Welcome to Simulation, Part 1. Today we will focus on dynamic display, kinematics, and animation. This lecture forms a foundation for computational physics by showing how to visualize models effectively. Our learning outcomes cover the anatomy of a simulation and how to choose appropriate scales. We will build simple kinematic simulations and animate them using both frame-by-frame updates and Matplotlib's Func animation. We begin by importing the necessary libraries, including NumPy for calculations and Matplotlib for plotting. We also import display tools to handle our animations. The output confirms our imports are complete. Note that animation rendering is turned off by default to keep the notebook fast, but we can enable it during a live demonstration. Every simulation requires state variables, parameters, and an update rule. It is crucial to choose natural time and length scales so that the visual display accurately reflects the physical motion. Our first example is a one-dimensional particle moving at a constant velocity. The update rule is simply the initial position plus velocity times time. Here we set up the simulation box and generate random but reproducible initial conditions. We calculate the time of flight based on the box length and maximum velocity. This continuation of the code calculates the position array over time. It also prepares the plotting commands to visualize the constant velocity trajectory against the right boundary. The output stream displays the generated initial conditions and the calculated time of flight. This confirms that our particle will reach the boundary within the expected 5 seconds. The plot clearly shows a linear relationship between position and time, which is exactly what we expect for constant velocity. The particle successfully hits the 10-meter boundary mark at the end of the simulation. Next, we introduce frame-by-frame display using IPython's display tools. By repeatedly clearing the output and drawing a new frame, we can create a simple animation loop. This code defines a function to draw a single frame of the particle's position. It sets up the figure, plots the point, and fixes the axis limits so the background remains stable. Here we implement the live display loop. If enabled, it iterates through the position array, displaying and clearing frames with a short delay to mimic continuous motion. The output shows the final frame of our particle display. In a live setting, you would see the dot traverse the horizontal axis smoothly. We can easily extend this concept to many particles. By replacing single numeric variables with NumPy arrays, we can simulate multiple trajectories simultaneously without using slow Python loops. This code generates random initial positions and velocities for 8 particles. Thanks to array broadcasting, the entire set of trajectories is computed in a single efficient line. The resulting plot displays the distinct linear paths of all 8 particles. The varying slopes represent their different constant velocities as they travel over time. Our second example models a simple pendulum. We use the small angle approximation, where the angle follows a cosine function, and then map this to Cartesian coordinates for plotting. We define the physical parameters, including gravity and the pendulum's length. We then calculate the natural angular frequency and the corresponding period of oscillation. Here we generate the time array and compute the angular displacement. The trigonometric mapping then converts these angles into x and y coordinates for the bob. This code section finalizes the plotting commands. It sets up the axes to show both the angle over time and the spatial path of the pendulum bob. The stream output verifies our calculated angular frequency in a period of roughly 2 seconds. The initial angle is confirmed to be 5 degrees. This first plot shows the angular motion over time, displaying a perfect sinusoidal wave. The constant amplitude reflects our ideal, undamped kinematic model. The second plot visualizes the physical arc of the pendulum bob in the xy plane. This confirms that our coordinate transformation correctly mapped the angle to a curved spatial trajectory. Moving to 2 dimensions, our third example covers projectile motion. We use the analytical kinematic equations for constant gravitational acceleration to trace the flight path. We decompose the initial velocity into x and y components based on the launch angle. We then estimate the time to maximum height and the total flight time to set our simulation bounds. This code computes the full coordinate arrays for the projectile and calculates the theoretical range and maximum height. It also prepares the final visualization. The output lists the key flight metrics, including a 3.17-second total flight time and a maximum height of just over 12 meters. These values provide a sanity check for our physical model. The plot displays the classic parabolic trajectory of a projectile. The path starts at the origin and lands perfectly at the calculated range on the horizontal axis. We now shift to a more robust animation technique using Matplotlib's Func animation. This method is highly efficient and integrates beautifully with Jupyter notebooks. This code sets up the figure and the line object that will be animated. The initialization function clears the data, ensuring a clean slate before the animation begins. The update function modifies the data for each frame. We then pass these components into Func animation to generate the video object. This code finalizes the animation rendering process. It converts the animation object into an interactive HTML5 video player for the notebook. The output generates an interactive video player, allowing us to scrub through the particle's motion. We now transition to our final example, a traveling sinusoidal wave. A traveling wave requires both spatial and temporal variables. We define the wave speed, wavelength, and calculate the wave number and angular frequency. We generate the spatial grid and evaluate the wave function at time 0. This provides the initial state before we apply any time evolution. This code prepares the animation framework for the wave. The update function shifts the phase of the sine wave based on the current time step. Here we compile the wave animation using Func animation. We then request the HTML representation to display it dynamically. The stream output confirms the wave parameters, including a wave speed of 2 meters per second and a wavelength of 4 meters. The static plot shows the initial snapshot of the wave at time 0. The clear sinusoidal shape serves as a baseline before animation. This code block finalizes the rendering of the wave animation. It ensures the HTML video player is properly instantiated in the output cell. The output provides the interactive player for the traveling wave. We also move on to discuss common mistakes and good practices in simulation. Common pitfalls include choosing poor time steps or hard-coding values instead of using variables. Always ensure your visual scales match your physical parameters to avoid misleading plots. For guided practice, try altering the initial conditions in the provided examples. Increase the pendulum's initial angle or change the projectile's launch velocity and observe how the plots respond. In summary, we explored dynamic displays, kinematic equations, and Matplotlib animations. In the next part, we will transition to force-based simulations using Newton's second law.